Okay, good morning, everybody. We are going to do one more example together of curve sketching. And again, we're going to pick one that's kind of hard to predict. I don't look at that equation and just go, oh yeah, I know that shape. There's people who could, certainly. I'm not one of them. So what do I have at my disposal? I have the tools of calculus, and I know that the first derivative, and playing with that, is going to answer A and B, and I know the second derivative is going to answer C. So let's start there. Let's start with the first derivative of this thing. And oops, hang on, I forgot my stylus. While I'm going to go get my stylus, feel free to get started on that first derivative. There we go, got the stylus. And away we go. Okay, so for A, let's start up here. I'm going to try to conserve room here. So starting for A, I would like f primed of x. Okay, I'm going to make this a little bigger too. There we go. So f primed of x. What do we know about f primed of x? Well, it's quotient rule. So denominator times the derivative of the numerator minus numerator times the derivative of the denominator all over the denominator squared. All right, let's simplify that down a little. That's going to give us x squared minus 2x squared, and then positive 1. So I can write that as 1 minus x squared all over x squared plus 1 all squared. Can I simplify that anymore? Not really. If I factored a negative 1 out of here, that still wouldn't be the same factor as this, because then the 1 would become negative. So no, there's no canceling I can do with that. That's about it. That's the best I can do with that. Okay, so what do we know? We know we have critical values. If we're going to figure out where we're increasing and decreasing, we have to check the intervals between the critical values. And then, once we've done that analysis, we'll know if those critical values are local maximums or local minimums. So we need to figure out where f primed of x is 0. So we set our derivative to 0. And then we multiply both sides of the equation by the denominator, which basically makes it go away. And then we're going to move everything to this side so that we end up with something easier to factor. And we realize that our critical values happen. Let's factor that. That's a difference of squares. Critical values happen at negative 1 and 1, right? So therefore, those are our critical values. So those are the intervals that we are going to explore. So we're going to do an interval diagram. So intervals. And we're going to explore the intervals from negative infinity to negative 1. The interval between negative 1 and 0, or sorry, and 1, I meant to say. The interval greater than 1. So there we go. So there's, because those are our two factors, right? So those are our intervals, and those are our two critical points. So our factors are x plus 1 and x minus 1. And that will tell us what's happening to the derivative. And from that, we can conclude whether we're increasing or decreasing on the original function itself. So pick a number less than negative 1. How about negative 2, which makes that negative, a negative times a negative is a positive. So the function's increasing from negative infinity to negative 1. Between negative 1 and 1, I guess 0 is the logical choice. That makes this a positive, this a negative, which means the overall behavior of the derivative is negative, which means that we are decreasing between those 2 points. Pick a number bigger than 1. 2 seems reasonable. So 2 makes this factor positive, that factor positive, which means the overall derivative is positive, and that means that we are again increasing. So my A answer, just to summarize, is, I'll say therefore, we are increasing. And I like to use interval notation for this. So we're increasing on the intervals from negative infinity, right, less than negative 1, up to negative 1. Yes, that has to be a curve, right? Because we actually aren't increasing at -1 because that's, where the slope is 0. And we're also increasing, I'll put a dot there, we're increasing when we are bigger than 1, right? So there's our two places where we're increasing, and we are decreasing between -1 and 1. So there we go. We've answered A. Now, are those local maximums and local minimums? Well, yes, they are, because if you change from increasing to decreasing, that means that point is a local max. So for the B answer, I can say that -1, and okay, let's figure out the actual x or the y coordinate of that. Oops, I didn't mean to do that. Go away. There we go. The y coordinate of that, when x is -1, I get -1, and then I get 1 plus 1, so I get -1/2. So -1/2 is a local, right? It was on the way up, then on the way down, increasing on the left, decreasing on the right. So it's a local maximum. And the next point, when x is +1, and run the math on that, you'll get 1/2. Well, that's at -1. At +1, we're decreasing on the way there from the left, but we're increasing after we leave it on the right. So that is a local minimum. So there we go. We've answered A and B. That's what we know. Let's move on to part C. So part C, we need to know what the second derivative is. So for part C, we're going to have to find f prime primed of x. So let's see what we can find. So here's f primed of x. So that's 1 minus x squared over x squared plus 1 squared. So low, oops, go away. Come on. Low times the derivative of high minus high times the derivative of low. Now the derivative of this thing here is going to need chain rule, right? So that's going to be 2 times the actual u itself, the inside itself, to the power of 1 this time, and times the inside of the bracket derived. There we go. All over, and now the derivative rule here says that the denominator gets squared again, so that's now to the power of 4. All right, I certainly don't want to work with it like that, so I'm going to try to simplify it a little. And the tool in my toolbox that I almost always kind of go to first is factoring. I think I'll leave the negative with this factor here, and I'm just going to factor out 2x. So I can take a 2x out of here, I can take this 2x here, so I can factor out a 2x. I can also factor out an x squared plus 1. There's 2 of them in this term, there's 1 of them in this term. So I'll factor one of those out. So what does that leave behind? From this first term, it leaves behind the negative, and it leaves behind 1 of these x squared plus 1 factors. This negative also got left behind, and I didn't touch that factor. I didn't touch this 2 as a factor, but this has already been factored out. It's right there, and this has already been factored out. It's over there, so that's it. And the denominator, I haven't done anything to yet. So take a second and see if you can understand what I did there. I'm kind of crowding my work. Sorry if that makes it hard to read. Any questions on how I did that? Good old quotient rule and chain rule. All right. What can we do now? Well, now that factor can cancel one of those, leaving 3 of them behind. And in the bracket there, I can simplify that. I can simplify this to, let's see, that'll be negative x squared minus negative 2x squared, which is 1x squared. And it'll be negative 1 minus 2 times 1, so it's x squared minus 3, all over x squared plus 1 cubed. And there we have it. There's our second derivative. Great. So what does that tell us? Well, here's what we know. We have to explore now. What I've been doing in previous examples, because the second derivatives in the previous examples have actually been fairly less complicated than this, let's say, I've been just kind of saying, all right, let's explore when that's greater than 0 and when that's less than 0. And I've just been doing that directly. But notice here that's going to be really hard to do. I think this time I'm going to actually break out an interval chart. Here's what I know. I do know that the intervals I have to explore are the critical values of this. So again, I want to think about, well, okay, where are my zeros? Because I want to figure out when am I increasing or decreasing? When am I above 0? When am I below 0? So when is f prime primed of x equal to 0? That's what I'm trying to think about. Well, notice that this denominator will always be positive. Can you see why that is? Because no matter what number you put in here, you square it, you add to 1, which makes it even more positive, and then you cube it, which won't change its positivity. Positivity? Yeah. So there we go. So that the denominator is always positive. So really, all I got to worry about is the numerator, and the numerator here will be 0. So f prime primed of x will equal 0 in two cases. When x is 0, right, because that would turn this factor into a 0, and when x squared minus 3 is 0, I'll maybe even say when. There we go. And that would mean then that x is equal to plus or minus root 3. Right? I'm not going to factor that thing, obviously, because I'd be dealing with a radical. I mean, I could, but if you'd like to see it in factored form instead, I could just say it's x plus root 3 times x minus root 3 is equal to 0. So same thing. So there we go. So I have actually 3 kind of points that could be inflection points. I don't know for sure that they are yet until I know if I change from going greater than 0 or less than 0, right? If I'm curving up, then curving down, or concaving up, then concaving down. So I think the way to explore that is to make yet another interval chart. So the interval charts now, so this is going to be a little bigger than the last one. So now my interval chart is, okay, what's the smallest of my numbers I'm exploring? Negative root 3. So what happens when x is less than negative root 3? Next interval, what happens when x is between negative root 3 and 0? Next interval, what happens when x is between 0 and positive root 3? And my final interval I got to worry about is what happens when x is more than root 3. All right. Now, what factors do I have to worry about? Notice this factor down here I'm not even going to bother with because it's always positive. So I'm only going to worry about the 2 numerator factors. 2x and x squared minus 3. And multiplying those 2 things together will tell me what the behavior of f prime primed is, whether it's increasing or decreasing, which tells me whether the function is concave up or concave down. So let's see. Pick a number smaller than negative root 3. How about negative 2? That would make this negative. It would make this positive, which would make the curve itself, the derivative of the curve negative, which means that we are concave down from negative infinity to negative root 3. Okay. Now let's pick a number between negative root 3 and 0. How about negative 1? Because root 3 is like 1.7 roughly, I think. So negative 1 would be a good pick. Negative 1 makes this factor negative. It also makes this factor negative, because even though you square a negative 1 and get a positive, that's still smaller than 3. So negative, and a negative times a negative is a positive, so we're concave up in the interval from negative root 3 to 0. That's a 3. Sorry. Terrible writing. There we go. All right, pick a number between 0 and root 3. How about 1? 1 would make that factor positive. It would keep this factor negative, and that means that the overall behavior of the derivative is negative, which means we're concave down again from 0 to root 3. And finally, pick a number bigger than root 3. 2 sounds good. 2 times 2 is 4, which is positive. 4 minus 3 is positive. Positive times a positive is positive, which means we are concave up again from root 3 to 0. So the critical point here of negative root 3 is where it changes from concrete down to concrete up. Therefore, it is a point of inflection. So negative root 3 is a point of inflection. I might go back to my original function here. Let's see, what happens when you plug in negative root 3 to that? Let's get the y coordinate. Well, the top will be negative root 3. When you square a square root, you just get, what would that be? Negative 3, right? So negative 3, hang on a sec, let me think about that for a second. F of negative root 3 is negative root 3 over negative root 3 squared plus 1, which is negative root 3 over 3 plus 1. So it's actually negative root 3 over 4. There we go. To do some scrap work there. Too tired in the morning to do that mentally. So this is negative root 3 over 4. So there's one point of inflection. What happens at the next critical value? At the next critical value of 0, we go from concave up to switch to concave down. So that's another point of inflection. And that one's easy, 0, 0, because the numerator is just x, right? And then the next one is what happens when x is root 3. Well, at root 3, we switch from concave down to concave up. So that's also a point of inflection. And the math would work out the same. It would just be positive. So there's my points of inflection. And I do have to sketch a graph of this. So just to estimate, that's around negative 1.7. And let's see, 1.7 divided by 4, 17 divided by 4 would be 4. So it's going to be close to like negative 0.4 roughly, right? Okay, so I think we're ready to graph. Oh, you know what? No, we're not. We're going to do one more thing. One more thing before we graph. You know what else I would do before I sketch a graph is I'd also check the y-intercept, but we kind of already got it. The y-intercept is 0. What about the end behavior? See, remember when I was graphing the other examples we were doing, I was mostly doing cubics, right? And I always knew that a cubic looks like this if it's got a positive leading coefficient, right? On the left side, it goes down to infinity. On the right side, it goes up to infinity. So I'm going to try to figure out what the end behavior is for my original function. And it was x squared plus 1, right? That's how good my memory is. Yes, it was. So what's this thing doing as you go to the left and right on the graph? I kind of can't tell just by looking at it. And you know what else this would tell me, by the way? When I ask what is the end behavior, I'm also asking, are my local max and min absolute? So I'm actually answering that question too, if I can tell what this thing does as it goes to the left forever and to the right forever. Hey, have we in this course ever done something like that, where we looked at functions and equations and tried to figure out what they're doing as they go forever to the left and forever to the right? Anybody remember what I'm talking about? It's been a while. What am I talking about? Feel free to put it in the chat. What calculus operation do I have to perform here? We're doing limits to infinity. So let's do some limits. What is the limit as x approaches? Let's go to the left first. Negative infinity of x over x squared plus 1. Remember how we approach that? What we do is we divide top and bottom by the largest degree of the variable in the function. So that's going to leave me with the limit as x approaches negative infinity of 1 over x and 1 plus 1 over x squared. Okay, now some people really struggled with this concept, but it's a fairly simple idea if you think about it. It's not just, hey, the algebra tells me this. You have to reason it out. Okay, as this thing here goes infinitely big, it's 1 divided by an infinitely big number, or actually I should say it's an infinitely small number, like it's negative 10, negative 100, negative 1,000, negative 1 billion. This top will always be, it'll always be basically 0, right? It's 1 over a number that's so incredibly small that when I plug it in, it's 0, but it's coming at 0 from the negative side. It'll always be a negative value. It'll be negative decimal 0.00000. You get the idea. The top is negative. The bottom is 1. So I have a number that's 0 for my answer, but it's 0 approached from the negative side, right? So I am approaching 0 from the negative side of the x-axis. That's my limit. And the limit as we head to the right forever, just go back to here, and I can just go right to here. The math's the same. It's, again, 1 over x over 1 plus 1 over x squared. And that's going to be 0 from the positive side over 1. So that's going to be 0 from the positive side. So there we go. I now can put all of this information into my graph. Does everybody get again why this is just 1, right? And why this is 0, but it's approaching 0 from the negative side. So let's put all this information. Okay, what do we know? Well, we know, let's see. We know 0, 0 is a point of inflection. We know we have another point of inflection at, what was it again? What was it again? It was negative 1.7 and negative 0.4. I got to estimate that. There's negative 1.5, 0.6, 0.7 maybe there, and 0.5 would be halfway, so not quite halfway. Somewhere there. Good enough. And then same thing on the other side. But it's on the positive side of the axis, though. So it's 1.5, so 0.6, 0.7, maybe about there, not quite halfway. And again, not quite halfway up. Roughly there. So there's my points of inflection. That's where the curvature changes its concavity. What else do I know? Oh yeah, I have local maximum here at 1, 1/2. I have a local minimum here at negative 1, negative 1/2. I think I'm ready to draw this thing. It's got an inflection point, so it's concave up here, and then it's concave down starting there, but it's still heading towards infinity. Right? It's heading towards 0, but from the positive side. Here, it changes direction, so it was concave up here, now it's concave down. And it's still concave up now, or sorry, it was concave down here, now it's concave up, but it changes there, and it heads that way. I don't know how that's, what do you think? Let's have a look. Let's see what Desmos thinks of my beautiful graph here. Compared to Desmos, what do you think? Okay, well, again, I have a wider scale, so there. Pretty good. I think I got this, right? Let's put the points down, right? There's my point of inflection. There's my other point of inflections. Yeah, pretty good, right? We changed direction of concavity. That's kind of hard to see on this graph. I kind of exaggerated it. It's actually a more subtle concavity change when you look at it on a real graph than my sketch was. But I'm still pretty proud of my sketch. I think it's still a good sketch. Let's see, do I have the right max and mins? Yeah, I do. I have the right 1, 1/2, negative 1, 1/2. And there you go. That's curve analysis so far in this unit. So some of the questions that we've assigned are like this. They take a whole lot of minutes to get through because you have to think about all of these things. And then when you're done, I do actually very much encourage that you kind of check to see if you've got the right sketch from Desmos. And if you don't, you got to go back and go, okay, what did I analyze wrong? Okay, so that's how this stuff works. This is, I think, some of the most fun stuff we do in this course, right? You really get to apply the stuff, and you get to play detective and kind of try to say, okay, use your imagination. What is this curve going to look like? Okay? So, I kind of exaggerated how fast this curves down, obviously. Let's see. It's not too bad. I think I might have counted this point a little too low, too. Oh, well. You get the... Yeah, oh, yeah, it's definitely too low. Because this is a half, right? So, oh, yeah. Okay, I'm gonna redraw that. This point's way too low. If this is 0.5, 0.4 is maybe about there. Yeah, there we go. That's better. And then changes concavity, but it's heading that way. So this guy's too low. See, that's a mistake right there. It's like, oh, apparently I can't count to 0.5. 0.5 is here, so 0.4, again, that'd be 0.5, 0.6, 0.7. 0.4 might be about there. So we are concave down, concave down, concave down, concave down. Then suddenly we're concave up, but we're heading towards 0. There we go. That's why. I'm way more proud of it now. There we go. Definitely counted those points wrong. Cool. All right, I'm going to stop my video.